Hello and welcome back to CMOS RF integrated circuits. Today lecture 5, this is part of the second module on passive RLC networks. Today we are going to discuss matching. So far in the last 4 lectures you might have heard of this word several times. So, we have said we need to match the load to the characteristic impedance of the transmission line, or we have made statements like we need to match the source impedance to the characteristic impedance of the transmission line, or we have made statements like we have to match the load to the source impedance to get maximum power transfer. So, we have made these statements several times, and today we are going to start learning about how to do such a thing, how to achieve such a goal. All right. Now, let us consider the following. Let us say I have a source which is inseparable from a source resistance, and I have a load. Now, for maximum power transfer given R s, R L has to be equal to R s. This is for maximum power transfer. What if R L is not equal to R s? What do? Do you give up? Alternatively, what we could do is we could conceive of a network in between this network is made purely out of lossless elements. What do you mean by lossless elements? Inductors, capacitors, if you need transformers, mutual inductances, any element that does not consume power. So, this does not mean that you can use transistors, you cannot use resistors, you cannot use transistors, diodes, nonlinear components, anything that consumes power, you cannot use inside this network. So, suppose I do this, suppose I make a lossless network, I put it in between the source and the load like I have drawn, and suppose I make sure that the impedance looking in to the lossless network at the point that I have shown, this impedance is equal to R s. Suppose I can achieve this. If I manage to achieve this, then I will get maximum power going into the lossless LC or LC transformer mutual inductance, this lossless network. So, maximum power is transferred into this network. Now, this network is made out of components that do not consume any power. So, all of that power is delivered to the load. So, I still get maximum power transfer from the source to the load. So, the design of these lossless networks is called matching. This network is called a matching network. Now, let us try to understand this. What if inside this lossless network I basically use a transformer, an ideal transformer? You have all studied transformers in your circuit theory courses, hopefully you have. Now, if the transformer has a turns ratio of n, n turns on the primary, 1 turn on the secondary, or vice versa. I mean, let us just choose this. Let us say that the turns ratio between the primary and the secondary is n is to 1, n can be less than 1. All right. What is the input impedance that I see looking into the primary? How do you figure this out? Well, it is what you might remember is that if the primary voltage is V primary, then the secondary voltage is going to be V primary by N. Yeah. If the primary current is I primary, then the secondary current is going to be what? I primary times N, because power needs to be conserved. So, the power delivered to the transformer on the primary side is I p times V p. The transformer does not consume any power, it delivers all the power to the load. So, the power delivered to the load is V p by N times I p by N, which is again V p times I p. All right. So, that is how it works. So, the transformer is a lossless network. Now, given these circumstances, what is the resistance, what is the impedance that you see looking into the primary? You apply a voltage V primary and you see that the current is I primary, right. The current is I primary. So, the impedance looking into the primary is V primary by I primary, right. And what is the relationship between V primary and I primary? We know the relationship at the load. At the load, V primary by N equal to I primary times N times R L. So, therefore, V primary by I primary is N squared times R L. So, therefore, Z in is equal to N squared times R L. And what you can do is you can choose N to be equal to square root of R s by R L. If this is the relationship for N that you choose, then you get exactly what you need. You get Z in is equal to R s. So, you get maximum power transfer into the primary of the transformer. All the power delivered to the primary of the transformer goes to the secondary and therefore, to the load, because the secondary also does not consume any power, right. Is this okay with everyone? All right. What is the catch here? What is the big problem? Why do we need to study matching networks if it is so easy, if I have already finished off the topic in 5 minutes? There has got to be a catch, it can't be so easy. The catch is that I assumed that I have got an ideal transformer. Does not exist. It is impossible to make an ideal transformer. We are going to study transformers later on, but it is not possible, right. Second thing is transformers also consume power. It is impractical to say that I am going to make a transformer and it is not going to consume power. There are going to be copper losses, there are going to be core losses, So, because of these things the transformer is not going to be lossless anymore, right. Between each winding of the transformer there is going to be a parasitic capacitance. Between the primary side and the secondary side there is going to be a parasitic capacitance. So, the transformer is a mess. The ideal transformer is just a mathematical entity, it is not possible to make such a thing. All right. So, wish for an ideal transformer, it is not possible. So, therefore, we have to continue our study of matching networks. Now, if I have a network which is made out of inductors and capacitors in front of a load resistance, is it possible to have the input impedance to be a resistor? It is not possible. Why not? Because there are frequencies at which the input impedance will be inductive, there are frequencies at which the input impedance will be capacitive, right. It is never going to be that the input impedance is going to be R s all the time, unless there is no L and C and R L is already equal to R s, which is a trivial case, but otherwise it is just not possible to have the input impedance equal to R s all the time at all frequencies. What is possible is to make a network which at discrete interesting frequencies works in the fashion that I have shown. So, it is possible to select certain discrete frequencies, let us call them f1, f2, etc. Only at these frequencies the input impedance of the entire network is actually equal to R s. At other frequencies we do not know what is going to happen. Okay? Important is that these frequencies are discrete, it is not a range of frequencies, it is a discrete frequency. Fine. So, it is possible, like we saw in the earlier discussions, we were trying to transform inductor in series with a resistor to inductor in parallel with a resistor. It is possible to do that at a discrete frequency, not at all frequencies. Similarly, this network can be transformed into a resistor at a discrete frequency. All right. So, given that, what can be the easiest network that we can think of? Let's think of the following. So, this is the matching network. I have got an inductor, I have put an inductor in parallel to the resistor and I have got a capacitor in series with that. Okay. Now, we can transform the inductor in parallel with the resistor to a series combination of an inductor and a resistor at a given frequency. Let us say I choose the frequency omega 0. All right. So, let us say I choose this frequency omega 0, then the inductor in parallel with the resistor can be transformed to an inductor in series with a resistor. And what is the relationship? What is L prime R prime R L prime? You go back to the discussion in the previous class. Yeah. So, this is what we had done in the previous class. You remember, we had an inductor in parallel with a resistor, which we could transform to an inductor in series with a resistor, and vice versa. And the relationship between L s and L p was over here, the relationship between R s and R p was over here. Okay. Before we go into what is Q, let me finish the story and then we will talk about the Q over here. Do not even try to guess what Q is. Okay. So, we do this transformation. So, it is conceivable to do a transformation inductor in parallel to resistor to inductor in series with the resistor. Then the network that we end up with is a capacitor in series with the inductor in series with the resistor. Now, at omega naught, if I place a capacitor such that at omega naught this capacitor resonates with the series inductor, then the series combination of the capacitor and the resistor and the inductor becomes an impedance of 0 ohms at omega naught, which means that what I see as my load is R L by 1 plus Q squared. So, pick C such that at omega naught this is the relationship. Okay, pick C in this fashion and then C and L will resonate, they will form a combined impedance of 0 ohms at omega naught, and therefore, all that you are going to see is R L. Am I right? So, if you do such a thing, then your load resistance at omega naught is going to be R L by 1 plus Q squared. . So, looking in over here, what I see is R L by 1 plus q squared. I want this quantity to be equal to R s. So, therefore, I want this quantity, I want the input impedance of the network to be equal to R s. So, by design R s should be equal to R L plus 1 plus q squared for maximum power transfer. Therefore, q is going to be equal to square root of R L by R s minus 1. Yeah, that is correct. So, you compute the q. So, this is how we go about doing this, proceeding with our story. Number 1, compute the q needed. Q is going to be this. Step 2, compute L. What is the relationship between Q and L? Inductor is parallel with a resistor, the Q is omega naught L divided by R L, right. So, L is going to be Q times R L divided by omega naught, that is at the chosen frequency omega naught. And step 3 is compute C. So, we went backwards in our derivation, in our explanation. So, C is this. C is going to follow this equation. You know L, Q and omega naught. So, you figure out what C is. All right. What is the problem? What is the biggest problem with this step 1, step 2 and step 3? What is the problem in step 1? What happens if R L is smaller than R S? If R L is smaller than R S, then I do not get a meaningful number for Q, I get Q to be imaginary, in which case we are stuck. Okay. So, this technique works only when R L is greater than R S. So, when R L is lesser than R S, we have to figure out some other matching network. This matching network is not going to do my job. So, what else can you think of? We just picked something up and it seemed to work. Pick something else up. Let us pick up this. Here I can transform the series combination of the inductor and R L into a parallel combination of an inductor and some other resistor. Okay. And The expression for that is also quite straightforward, it is exactly the converse of the old expression. So, all right. So, this was exactly the opposite of the old expressions. I do not need to rewind back all the way to the previous class to figure this out. The easy way to remember these expressions is as follows. The inductor value is hardly going to change. So, it is going to be 1 plus q squared by q squared, or it is going to be q squared by 1 plus q squared, q is large. The resistance value needs to be small if it is a series resistance, it needs to be large if it is a parallel resistance. So, accordingly you figure out whether it is divided by 1 plus q squared or multiplied by 1 plus q squared. Fine. So, we transform the inductor in series with the resistor to an inductor in parallel with the resistor, and now I need L prime and C to resonate with each other at omega naught. So, if C and L prime resonate with each other at omega naught, then the parallel combination of L and C, L prime and C is an infinitely large impedance, which means that you do not need to consider it at all, which means that all that you are left with in your network is R L prime, right. So, therefore, by design R L prime has to be equal to R S for maximum power transfer. So, therefore, you can figure out what is the value of Q that you need. Once you have figured out what is the value of Q you need, you can figure out what is the value of L, because L in series with R L means, what does it mean? That the Q is going to be equal to R by omega naught L. No, exactly opposite, omega naught L by R. I think yeah, this is wrong. How do you remember which formula is for what? When you have inductor in parallel with a resistor, the larger the resistance, the more the Q. You really do not want the resistor to be there at all. You want infinitely large impedance instead of the resistor for infinite Q. So, therefore, when inductor is in parallel with resistor, resistance comes in the numerator, which means Q increases as the resistance increases. When you have inductance in series with a resistor, when you decrease the resistance, when you make the resistance a short circuit, you get infinitely large Q, which means that you need the resistor in the denominator. Okay, that is how you keep in your mind what the correct formula for Q should be, correct result should be. Okay. So, Q is going to be omega naught L by R. So, therefore, I can compute the inductor value that I need, this inductor value. Then C and L prime should resonate. L prime is 1 plus q squared by q squared times L. all right. Does this work, or is there a flaw here? Something like this. Okay. So, what are the problems here? This network, this matching network does not work when R L is more than R S, in which case the previous matching network works. This matching network works only when R S is more than R L. Fine. What else can we do? We can also conceive of doing playing with our networks. We can also conceive of doing something like this. As our matching network. Okay. And the derivation for this is also quite trivial. You just have to transform R in parallel with C to R in series with C. The value of C is not going to change much, the value of the resistance is going to go down by 1 plus q squared. And this capacitor, this transformed capacitor needs to resonate with the inductor and at the chosen frequency omega naught, and when it does resonate with the inductor at omega naught, then all you see is the resistance R L divided by 1 plus q squared, that is all you see, right. So, this is also going to work. So, q is always going to be more than 0, which means, or q is going to be a real number, which means that R S has got to be less than R L for this to work. And alternatively, you can also conceive of this. And it is straightforward to show that this will work only when R L is less than R S. Okay. So, here the series combination of C and R have to be transformed to a parallel combination of C and R, and then C should resonate, the transformed capacitance should resonate with the inductor value to get infinitely large impedance open circuit. The remaining resistance will be R L times 1 plus q squared. So, R s has to be equal to R L times 1 plus q squared, which means that R s has got to be more than R L for this to work. Okay. So, we have 4 matching networks. All of these matching networks are broadly called the L match. So, there is no more space to write over here, but all of those are called the L match. L is not because of inductance, L is because of the shape of the matching network. So, it either looks like this, okay, or it looks like this. And if you turn your head in certain directions, these patterns are going to look like an L, the alphabet L. So, it is called an L match. Okay. Is this the end of our studies of matching networks? Not quite. There are a lot of problems with this. Let me do a numerical, and that will kind of illustrate the problems. Okay. So, this is going to be a numerical. Suppose we are talking about the transmitter inside your cell phone, and suppose we are talking about GSM, right, and one of the bands of GSM is from 1.6 gigahertz to let us say 1.8 gigahertz. These numbers might not be exactly accurate, but let us say this is the case. So, the cell phone needs to transmit in any channel over the entire band. So, the base station will tell the cell phone at exactly what frequency to transmit, and that frequency could be anywhere between 1.6 and 1.8 gigahertz. Suppose this is quite a wide band, okay, and the output of my transmitter is basically a power amplifier, and the power amplifier, the end of the power amplifier would presumably look something like this. So, you have got an output over there, and suppose I have a 3.3 volt supply, then maybe this output can swing peak to peak from 3 volts to 0.2 volts, which means that the peak to peak swing is about 2.8 volts. Okay. And suppose that the base, you are far enough from the base station, quite far from the base station, and you are required to pump out a power of 1 watt. Suppose this is what we are working with. Now, the first question is, I have got 2.8 volts peak to peak. What does that mean? That means it is 1.4 volts amplitude. That means RMS, it is about 1 volt. 1.4 divided by root 2, that is about 1 volt RMS. So, I am choosing easy numbers for my numerical. Might not be the case when you do your numericals, but I am doing it with pen and paper. So, all right. So, I have got a 1 volt RMS signal. I need to pump out 1 watt of power. What needs to be my source resistance? What needs to be my load resistance? And here of course, you need to assume that you are doing maximum power transfer, because that is the best case, right. You are right, if you make source resistance lower and lower, you will win more and more, but that comes at a cost, right. Making the source resistance more, I am sorry, you can make the keep making the source resistance less and less, and you will keep winning more and more if you have a knob on the source resistance. But really making the source resistance less is not a good idea, because that means that your power amplifier will need to be burning more and more current, right. You need to have a larger and larger area requirements for the power amplifier to have such a low source resistance, lower and lower source resistance. So, I want to know what is the maximum source resistance, what is the load resistance, such that I get 1 watt of power on the load. So, to do that, you have to have maximum power transfer, which means the source resistance should be equal to the load resistance. So, if this is R and this is R, then I get half a volt over here RMS, which means V squared by R has to be equal to 1 watt, right, half V whole squared divided by R has to be equal to 1 watt. So, R has to be equal to 0.25 ohms. Thank you. Okay, so, this is the case where you get maximum power transfer. To reduce the source resistance further, indeed you can get more power out, you can get even more power out, but it is not advisable, because reducing the source resistance further and further is just going to blow up the size of the power amplifier. All right. So, this is what I have got. I have got a system which puts out a 1 volt RMS signal. It has a source resistance of 0.25 ohms, right. Unfortunately, the load is not 0.25 ohms, the load is the antenna which is broadcasting the message. The antenna looks like a 50 ohm resistor. So, I need a matching network in between that matches the source to the load, right. Okay, great. Now, one quick thing about the source can range in frequency from 1.6 gigahertz all the way to 1.8 gigahertz. So, let us say I choose the center frequency at which it should be a perfect match at. So, my center frequency is 1.7 gigahertz at which I want a perfect match. Okay. At the other frequencies it will not be a perfect match, but you know you will be doing quite well, fine. So, suppose this is the case, then I plan to make a matching network. I have got a large load resistance, a small source resistance. I need to transform the large resistance into a small resistance. So, I need to put something in parallel with it. It could be L, it could be C, it does not really matter. So, L in parallel with R transforms to more or less the same L in series with a much smaller R, right. Fine. So far so good. And what is the Q? That is the first step, right. Something like this. It can't be R s by R l, because R s is less than R l. So, that is about equal to R l is 50, R s is 0.25. So, R l by R s is about 200. So, square root of 200 is about 14. Square root of 199, it is about 14. Yeah, 196 is 14 squared. Okay. So, I need a Q of about 14, which tells me what is the exact value of the inductor, right. Once you know the Q, you can figure out the exact value of the inductor. 1.7 gigahertz times 2 pi, that is my omega naught. So, omega naught times L So, the resistance divided by omega naught times L is about 14. So, L is about 50 divided by 1.7 giga divided by 2 pi divided by 14. So, whatever that number is, that is your inductor value. If you have a calculator, this can be computed. I do not have one over here. Fine. So, you compute the value of L, that is the second step, and then the third step is this L is going to transform to another inductor, which is going to be about L into q squared by 1 plus q squared. So, q squared is 199, 1 plus q squared is 200, that is about the same L. Okay. So, the value of L remains more or less unchanged when you transform it from parallel to series, and then this inductor needs to resonate with the capacitor at the chosen frequency. So, C times L should be 1 by omega naught squared, and from this you can figure out what is the value of C that you need. All right. So, what is the problem here? The problem is this: the bandwidth of my circuit is related to Q, right. So, what is the bandwidth? It is the center frequency divided by Q. So, we have got 1.7 gigahertz as our center frequency, divided by Q is about 14. So, my bandwidth is a little above 0.1 gigahertz. That is the total width of the band in which I will be able to transmit reasonably good amounts of power. The match is going to be reasonably nice, right. The desired bandwidth is 0.2 gigahertz. The bandwidth that I am getting is 0.12 gigahertz, which is significantly lesser. So, this is my problem, right. So, once you start saying that no, I want to have control over the bandwidth over which I should be able to broadcast power, right, then you can't do with this L match. So, the L match has 2 degrees of freedom. It has 2 components, one inductor and one capacitor, right. And you need, so think about the mathematics, right. You have some design equations and there are 2 unknowns. So, you can at max accommodate 2 equations, because if you have more than 2 equations you need a third unknown. Okay. So, what are the 2 equations related to? The first equation, the first design equation is related to Q, and the second design equation is related to the center frequency. Okay. And the Q also happens to be directly related to the ratio of the load and the source resistance. Okay. So, once you are given the ratio of the load and the source resistance and you are given the center frequency, you are done. The design is frozen. You cannot do anything to tweak the bandwidth or the Q or anything else. It is all frozen. So, what can we do? Well, the way I described it, the solution is simple. I need a matching network which has 3 degrees of freedom, which means there needs to be 3 components, not 2. So, if I have 3 components, then I will have 3 degrees of freedom. Maybe these 3 components are L 1, L 2 and C, maybe they are C 1, C 2 and L, I do not know. And the 3 degrees of freedom are R L by R S, Q and omega naught. Now, Q is related to bandwidth. So, therefore, you can also say R L by R S, bandwidth and omega naught, however you please. Such matching networks could look like this. They could also look like this. Okay. You could also have something like this. Or like this. So, these two are called the pi match, because somehow the matching network looks like the capital Greek pi, okay. This looks like the Greek capital pi, the letter pi, and the bottom two are called the T match, because they look like the capital T, alphabet T. Okay. So, so far today in the class, in this particular lecture, we studied the L match, which looks like an L, and then there are the remaining two, the pi match and the T match. And the reason why we probably will have to go for pi matches or T matches are because we need an extra degree of freedom, the bandwidth. Okay. So, with this we are going to close today's lecture. We have studied the L match in quite detail. We also did kind of a numerical example of probably why you would want to do matching, etc., practical scenario. And I also pointed you towards the motivation of the development of the pi match or the T match. Okay. Thank you. With this, we will close this lecture. Thanks.